Hello. So this is a classic deflection problem, and usually the first stage would be to calculate the reaction at the support. Okay, so A and sorry, B and moment B. But in fact, here we don't need to do that because we are going to what we need is the equation of the classic curve. And if we say for x here, we have no need of the reactions because we take everything to the left of the cutting point. So x will be 0 here and L here. So let's start directly. Okay, so how does that work? So let's write the moment. Well, because what we want to do, ultimately, we're going to use the formula that I will bring during the solution. You should remember them by now, but just in case. So the good technique consists in calculating the moment at any point x. Well, here it's quite simple. There's only one load, and it's a direct moment, and it's on the left of it, so it's m0. That's all so far. Okay, then what we know is that if we integrate once, we get the following: EI, so where E is Young modulus, I is the second moment of area of the beam, times the derivative of the deflection, of displacement, is equal to integral of, we integrate that. X dx. Well, this is really easy here, it's a constant, so equal to m0 times x. Of course, the difficulty is to not forget the integration constant. So I'm going to call it C1 as a constant. So it doesn't make any difference. Okay. And then we have EI times I is equal to integral of the second integral of the moment. Okay, well, or the first integral of the slope, if you want. So simple to integrate, and we end up with m0 x squared over 2 plus c1x plus c2. Okay, so we have done stage 1, which is express the things. Well, by things, I mean the function y(x). That's good. Second, that's not finished because we need to determine the integration constant. Okay, well, what do we know? Well, we can apply boundary conditions. Here they are the following. When x equals L, well, we see that the beam is located on the wall. So that gives two boundary conditions. The first one is that the slope is equal to 0. The second one is that, you can put that like a minus, is that what this deflection is also 0. Okay, so that means that, well, we'll draw the shape later, but that tells us that not only let's use a different color to reproduce that be what we expect it to happen. In fact, I mean, I can already apply the moment here. A screwdriver, I turn. All right, so I'm going to put that top in compression and bottom in tension. We are very likely going to end up something like that. That's what I would expect to happen. So 0 displacement and also 0 slope. Constant. Okay, horizontal. Tangent to 0 to 0. So it's very, very powerful, these boundary conditions. So they allow us to resolve the interaction constant. So 0 equals, now that gives us m0 times x plus c1 equals 0, and that is equivalent to c1 equals, so not xl of course, c1 equals minus m0 times L. Okay, fantastic. So for the deflection, I end up with m0 over 2 L square plus C1. C1 is minus m0L. So minus m0L square plus C2 equals 0. And that we can relatively simply calculate. So that's going to be minus 2 over 2. So that's 1 minus 2 minus 1. So minus 1/2. So pass on the other side, C2 equals m0 L square over 2. Quite useful. Therefore, I can replace, and the elastic curve, that's the elastic curve, the equation of the deflection is y is equal to 1 over ei, which I can factorize a lot of m0, isn't it? You can factorize m0 over ei times, actually I'm going to factorize m0 over 2ei. Right, and x square c1x minus 2lx and plus l square. And we can even factorize that later. This is it's actually x minus l square. Not much. Okay, great. That's what we wanted. Done. Always, if we have time, nice. And that's the equation of the elastic curve. Now, the deflection of the free end is at x equals 0, so b y of 0, we can just replace x equals 0, we end up with simply L square equals 0 times L square divided by 2ei. And at NC, the slope at the free end, also we need to use the equation that we had before, okay? We just need to replace C1 and also divide by EI, and we end up with dy over dx, that's theta at 0, theta at 0. This is an approximation, but very close enough for small deflections and small angles, and that's going to be equal to m0x. So m00 simply equal to c1, isn't it? Simply equals to c1, and c1 is minus m0l divided by ei. Sorry, my graphics tablet is playing around. So m0 times L divided by EI. So let's check if it makes sense on the figures that we had done by simply looking at it. Yes, so we expect the deflection to be positive, absolutely, and we expect the slope to be negative, absolutely as well. Okay, so this is a basic example of deflection. Now this problem was very, very, very simple. We didn't even have to bother calculating the reactions, just the way the supports were arranged to the right of the bar. Okay, we are going to do a lot more of this type of problem in this session. So, well, we'll do them. And otherwise, any queries, please use the forum, and I'll try to explain there. Thank you very much.